All right, welcome to the session, week 4 of NPTEL course, uh, signal estimation for MIMO OFDM wireless communications. And in today's course, we will be continuing the multi-parameter estimation, which we left in the previous class. And we will be seeing the result of channel estimation in the case when we have a single receiver and we have multiple transmitters. So just to recollect, the multi-parameter estimation basically refers to that we are transmitting, say, H1, H2, and so on, some HM, but their amplitudes is constant over time. So I think in the last class I said that H is time varying. So actually we have H1, H2, and so on up to HM, but they are not varying with time. So that assumption is still remains. OK. All right. And our signal model is Y is Hx plus V, and we have a single receiver antenna, and we have M transmitter antennas, and such that their channel coefficients are H1, H2, so on HM, and we are going to compute the channel estimation in this case. So before we proceed to the channel estimation, there are a few important vector derivatives whose knowledge is necessary. So we will be seeing the those vector derivatives and how they will be useful uh, uh, in the channel estimation. Okay. So let f. So f is arbitrary function whose derivative needs to be computed. Okay. So we will be seeing two kinds of derivatives. So first we'll be seeing the linear vector derivative. And second we'll be seeing the quadratic derivative. So the linear derivative will be of the form some say C transpose H. And of course, we need to find a derivative with respect to H, right? Which is what has to be estimated. And C is some constant. And the quadratic derivative will be of some form H transpose X H. So this is kind of a 2-degree polynomial, right? And the linear is a single degree polynomial, right? Okay. So first we consider our function f of h to be in a linear form, say C transpose H, which is my linear in H, right? Linear in H. Okay. So what are my C? What is my C vector? So it is some constants C1, C2, so on up to Cm. And what is my H? It is my parameter vector. H1, H2, so on up to HM. And if you multiply them, so this is essentially what is happening. This is the dot product, right? This is the dot product of two vectors. Okay, so what you get C1 H1 plus C2 H2, so on up to Cm HM. Okay. Now, if you differentiate what the dot product which we have received with respect to individual channel coefficients, that is del f by del h1, del f by del h2, so on del f by del hm, you will see that we get C1, C2, and Cm, right? Straightforward. Or what you can also say is that if we differentiate the function which is a linear in H, right? And if we compute its derivative with respect to H, we are getting the constant, right? So what we can say, so this is a very important result, result 1. You can just number it. So that is del by del H of C transpose H is del by del H of H transpose C, okay, which is C itself. So this is very important. That is, if we have A transpose B and this is B transpose A, both are same. That is the derivative of both are same. Okay. The next important result which we need to derive the channel estimation is the quadratic vector derivative. So in this case, we have the f of h, which is a function in h, as h transpose p h. So here you can see this is a quadratic function in h, right? This is a quadratic, that is degree is 2, quadratic function in h. Okay. Also note that this P matrix, okay, it is a symmetric matrix. What is the meaning of a symmetric matrix? So a matrix is symmetric if the transpose of the matrix also equals to the matrix itself, right? So that then it is called a symmetric matrix. So how will we compute its derivative? So let us club h p of h into two parts, right? So say h transpose is if I say 1 and p times h say is the second, and now we are going to apply the product rule of derivative to differentiate. So what we'll get is del by del h of h transpose ph plus del by del h of h transpose p into h. Okay. And if you just consider this to be C, which we saw above, right? If we consider P into H as C, and similarly, if we consider H transpose P as C transpose, and then if we apply this result, like this result which we had obtained here, that is derivative of C transpose H is C. So what will we get? That derivative of this is C. What is C? P times H. And here, what is C transpose? It is this is C, H transpose P is C, and its transpose. Okay. Now, here what you should know, this identity A B transpose is B transpose into A transpose. So if we do that and open, so you will get P times H plus P transpose H. Okay. If you take H common, you get P plus P transpose. Right. Now, this is for a general P. Okay, this is for a general P matrix. So if P is considered to be a symmetric matrix, if P is considered to be a symmetric matrix, that is, if P is equal to P transpose, in that case, the derivative reduces to twice of P into H. Okay, so this is a very important result. This is our second important result. Okay. So we have obtained two important results so far. So one is the linear derivative and the second is the quadratic derivative. So now we come back to our problem which we have. So our problem is what? That y is hx plus v. Okay. Now, if you take the expectation of this y, right, since expectation of v is 0, right? So expectation of y is x times h. Now, we also know the PDF of the noise, right? So it's a multivariate Gaussian. Okay. So the noise is a multivariate Gaussian. And how do we get y minus h squared? Right? How do we get this? So if we consider y is x times h plus v, and we have this is the PDF of noise, right? E to the power minus 1 by 2 sigma square into summation of v squared, right? This is the PDF of vector v, right? This is a joint PDF of all noises. And basically, what is summation of v squared? So v transpose v is basically summation of v squared, which is also which can be written as the norm 2 norm of v squared. Okay, this is the L2 norm of v. We had discussed, I believe, in week 1 or in week 2, what is the definition of L2 norm, right? So L2 norm. Okay. And since we have y is x times h plus v, therefore v is y minus xh. And this basically, if we substitute here, and this gets substituted here, right? So just follow the link. Uh, so we have the PDF. So this is my PDF in step 1. And from in step 2, we prove that summation of v square is nothing but v transpose v, which is the 2 norm squared of vector v. And in step 3, we say that since y is x times h plus v, so v can be written as y minus xh, and we substitute 3 in 2 and 2 in 1, right? And when we do that, we get this expression, which is my maximum of likelihood. Okay, so log has not come yet. So this is the maximum likelihood estimator, which is MLE, right? This is my MLE estimator, okay, which we have to maximize. So this is my likelihood function. This is my likelihood function. Now we take the log of this likelihood. Right? We take the logarithm of the likelihood so that we can perform computation easily. And because log is a increasing function, so it does not change the nature of the problem. So we take the log of the likelihood. And when we take the log of this likelihood, then what will you get? Minus n by 2 log of 2 pi sigma square and minus 1 by 2 sigma square y minus x times h whole square. So what we can say is that the maximum log likelihood MLE, maximize the log likelihood estimate, is equivalent. Okay, this is equivalent to minimizing, because this is negative sign here. This is a minus sign. So this is equivalent to minimizing y minus x of h squared, which is also called the least squares norm of the error. Okay, so why is this called least squares? We'll come about it. So what we said, so we had this expression, which was a likelihood expression. Say again, I'll say this is step 1, and we took its log of the likelihood in step 2, and we observed the log likelihood. And what did we see? That maximizing this L is equivalent to minimizing the second term of the log likelihood in step 2. And this is called the least squares problem. Okay. Now, how will we solve the least squares problem? This is the next point. So what is this? This is defined as y minus x transpose h transpose into y minus xh. Okay, this is the definition of a 2 norm squared. So if we have say an x1, which is say some a b c, right? So what will be x1 transpose? This will be a b c, and x1 into x1 transpose will be basically a square plus b square plus c square, right? It will be a square plus b square plus c square, and which is equivalent to under root a square plus b square plus c square squared, right? So this what we have written inside the bracket is actually the norm. This is called the norm operator, right? That is root of summation of all squared, right? This is called the norm operator, and if you are squaring the norm, that is why it is called least. Is the minima represents the least, and squares is the squaring of the norm, right? So that is why it is called the least squares estimator or least square operator. Now, again, if I say this is step 1, step 2, step 3. So in step 2, we'll basically first solve this transpose, right? So if we take transpose inside, we get y transpose minus again x times h transpose is h transpose x transpose. So just remember this property, a b transpose is b transpose a transpose. Okay, and into y minus xh, this remains as it is. And now when you multiply all the terms with each other, so you will get y transpose y minus this, and this, right? So this is what you get after multiplying. So now what do we have to do? Now we need to find out the derivative. Thing has happened. So, right. So just note that for vectors v and u, v transpose u is u transpose v. This is a property, right? Or you can a transpose b is b transpose a. Same thing. Okay, we are playing with vectors, and v transpose u is v transpose u transpose, which is u transpose v, right? Okay. So here, just note that now here, if you see, we have two terms. This is say a, b, c, d. So if you see, we are going to prove that term b and term c are similar, right? We are going to show that. So that is why if you see this, this term y transpose x h, and if you consider y as u and x times h as v, and if you take its transpose, right, and you will get h transpose xy. Okay, so these are just vectors properties. And so what will happen is that b and c term will merge together as one, so they will double up, right? So you get this 2 times h transpose x transpose y. Okay. So now this is my function, right? This is my least squares function which we need to solve. And what is our objective? We need to find h, which is my channel vector. Okay. So to find out this maximum likelihood estimate or the least squares estimate, now both are same. Okay, both are analogous to each other, both are same. So how will we do? We have to compute the derivative. of this function with respect to compute derivative with respect to h. So del by del h is 0, right? We need to equate the derivative to 0. So, and then we'll get it. So just remember the two results which we had derived above, right? So del by del h of say some c transpose h is c, and del by del h of some h transpose ph is 2hp. Okay, provided p is symmetric. Right? This is a important assumption. That is why we had twice hp. Okay, so if we differentiate it with respect to the results which we had obtained earlier, and equate it to 0, we will be getting h is x transpose x inverse x transpose y. Now this is a very important um, fun, fundamental result, which is also called as a Moore-Penrose pseudo inverse. Okay, this is a very important formula. Okay, so x transpose x inverse x transpose y. We will see why is it called a pseudo inverse. Okay, why is it called a pseudo inverse and why is it so powerful? We'll see this. So very interesting is that this pseudo inverse. So what is pseudo inverse? This stuff. Okay, so not the y part, but this x transpose x inverse x transpose, right? So this is called the pseudo inverse. And why is this the pseudo inverse? Why is it so interesting? Because it exists even for non-square x matrix. Okay, so you should know that if we have a matrix, right? We have say a matrix X, then its inverse exists, that is X inverse, only if X is square matrix, right? So if X is a non-squared matrix, then its inverse cannot be computed, right? So if we have a non-square X matrix, then its inverse cannot be computed. And that is where the pseudo inverse becomes very handy, because that allows you to compute the or manipulate the matrix in a way such that the inverse can be computed. And so it becomes very important. And it has another property that this pseudo inverse, right, which is x transpose x inverse x transpose multiplied with the vector x, results in the identity matrix. Now, what is the general form which we know that any matrix? Okay, let me not use X because that may confuse. Say A times A inverse is A inverse times A, which is I, right? So any matrix, if you multiply it with its inverse, then that gives the identity, right? So this is a this is basically so this even this basic identity rule is being satisfied by this pseudo inverse matrix, which is x transpose x inverse x transpose. And that is why this is called the pseudo inverse. Okay, we'll see further. So in this case, we have n is my number of pilot observations, right? So let's recollect the system model which we had. So we had some M transmit antennas, and we had a single receiver antenna. Okay, we had a single receiver antenna and we had M transmit antennas such that we had H1 to HM, which were the channel coefficients. Okay, so now what was happening is that when I say y is x times h plus v, so this x so basically at each time instant we are sending some symbol. So we have n pilot observations which are at n time instances, and we have m parameters, right, which are your m channel coefficient parameters. And ideally we take the number of pilot observations much more than the number of channels we need to estimate, right? So that we can get a sufficiently good number of, we have good observations to take the estimate. So in such a matrix, if n is my rows, right? And if M is my columns, then you will, if n is greater than equal to M, then this matrix is a thin matrix. Okay, this is a thin matrix if the since the number of rows is greater than the number of columns. If it is opposite, that is if the number of columns is greater than number of rows, then it is a fat matrix. Okay, so and obviously for n greater than M, that is strictly greater than M, right? X, this is your X matrix, right? This is your pilot matrix X, and this is not a square matrix. This is very important, right? Now X is not a square matrix if n is greater than M. When will X be square? Only if n equal to M, right? That is the number of rows equal to number of columns, and we have a square matrix. But what if n is greater than M? And in that case, we don't have a square matrix. So how will we compute X inverse, right? X inverse does not exist, right? How will you compute X inverse? X inverse doesn't exist. But now if you see this, X has a dimension of n cross M. Okay, X has a dimension of n cross M. And so X transpose will have a dimension of M cross N. Okay, X transpose will have a dimension of M cross N. And if you multiply X transpose X in, say again, one in one, if you see X transpose X will have a dimension of M cross M, right? Similarly, X transpose X inverse will again have a dimension of M cross M only, right? Now if you see X transpose X is having a dimension of M cross M, that is now this has become a square matrix. Okay, this is now a square matrix, and so its inverse exists. Right, so we compute the inverse of X transpose X, and that inverse also has a dimension of M cross M. And now when you multiply this X transpose X inverse with X, right, that is M cross M dimension is multiplied with the M cross N dimension matrix, you will get? You will get a M cross N matrix. Okay, you will get M cross N matrix. And if you multiply what you obtain in step 3, right, this X transpose X inverse X transpose, which we are calling as the pseudo inverse, right? This is my pseudo inverse. This is my pseudo inverse, right, which you obtain in step 3. And what is the dimension of pseudo inverse? It is M cross N, right? This is M cross N dimension, M cross N dimension. And if you multiply it again with X, okay, with the N cross M matrix, what do we get? We get a M cross M matrix again, right? Which and an identity matrix of M dimensions, right? So you have the diagonals as 1, and you have zeros on the non-diagonal element side. So what you see is that this pseudo inverse part, that is X transpose X inverse X transpose, uh, when multiplied with X, so this is analogous to X inverse X, which is identity, right? So say this is some M cross M, this is M cross M, and this is also M cross M, right? So in an ideal scenario, but since we have an N cross M matrix, and this is not a square matrix, right? X is not a square matrix anymore. So that is why we have to take the pseudo inverse so that we can find out the inverse of the matrix, right? So this is very important, and that's why I wanted to show you the dimensionality, right? How the dimensionality changes as you perform each and every matrix manipulation. Okay. Now, so now we have this estimate, which is the pseudo inverse, Moore-Penrose pseudo inverse, and now we will see what is the property of this Moore-Penrose pseudo inverse. And this is also the ML least squares estimate, right? So we compute, we had a first we had a maximize log likelihood, which was a normal MLE, and we converted it into a minimum of y minus xh. square, which was the minimum least squares estimate, right? So we converted a MLE estimator into a least squares estimator, and so now we are going to see what and we obtained that our channel estimate was is in this form, and now we are going to see its properties. So we have this estimator, and what is y, right? So y is xh plus v. Okay, xh plus v, and we substitute y, and if we again open and multiply, so we get these two terms, right? Term 1 and term 2, and if we solve this, we obtain this equation 1, that is h hat is I times h plus x transpose x inverse x transpose v, right? So say this is equation 1 which you obtain. Now if you take the expectation of this h hat, right? So expectation of h is h itself because it is a constant, so it comes out, and expectation of v is 0, right? So the second term vanishes, and what you are left with is expectation of h hat is h itself, and so this is an unbiased estimator, right? So now similarly for the covariance part, what, right? So how will you compute the covariance? So h hat minus expectation of h hat minus expectation of h transpose. And what is expectation of h? Expectation of h is h itself. Okay, so what will we get here? Expectation of h hat minus h hat minus h transpose. And from this equation, so if you basically take h to the left hand side, h hat minus h will be this term, right? It will be this term, x transpose x inverse x transpose v. So h hat minus h is this term. Okay, and we are going to substitute this term here. We are going to substitute this term to compute the covariance. So this is a bit of matrix manipulation again. So you can see it properly. You need to write it down on a paper and try to solve it yourself. So what you will get is that, and if you take this expectation inside, right, if you take the expectation inside, so the only source of randomness is my AWGN noise, right? So this expectation comes inside, and since all these are IID, okay, this is very important assumption which we are taking. So expectation of VV transpose is basically a diagonal. This is a diagonal matrix, right? This is a diagonal matrix, and this is basically sigma square into identity vector. Okay, so this sigma square into I. So this sigma square actually becomes it's like a scalar now, right? So you can play with sigma square. So sigma square now comes in the front. And again, if you perform some matrix manipulations, what you will end up is that, so this is basically your covariance. Okay, so this is sigma square x transpose x inverse. So if you just remember what we did in week 2 and 3, so if you possibly remember that for a single transmit antenna and a single receive antenna, and when you had to estimate this h, so this h hat had a variance of sigma square over x transpose x, right? So I hope you remember this. So this is very similar to what we have obtained here. The only difference is that since here we were playing with scalars, right? So this was a completely so since we are playing with scalars, and now we have a multi-parameter estimate. So now we have a matrix inverse, and here we did not have matrix inverse, right? Okay. So my estimate is a Gaussian such that its mean, right? This is my mean, which is h itself. So which shows again the unbiased unbiased estimator, and this is my variance. Okay. So quick summary. So we observe for a multi-transmitter single receiver concept. Okay, so just remember this is for a single receiver. That is, we have only one receiver at the end, only one antenna at the receiver. And for such a receiver, we obtain the H hat as shown. And this is my pseudo inverse. Okay. And we also see that H hat is Gaussian with mean H. And this is our variance. Okay. So any doubts in the concept? Any doubt? Okay, so if no doubt, I'll go to the problem solving. Okay, no doubt. So, right. So consider a maximum likelihood. So we have a multi-channel, multi-antenna channel estimation problem. Okay, and we have n received symbols, and the channel vector is having m parameters. Okay, so this is a multi-parameter estimation problem. So what he has asked is what is the ML estimate of H, right? So this is what we have studied so far. That is, if you have at multiple antennas, say M antennas in the transmitter, but you still have only a single receiver antenna. Right? How do you know we have a single receiver antenna? So in this problem, if you see you are receiving Y1 to Yn, that is at a receiver, you are receiving Y1, Y2, so on up to Yn, right? So, and N is my, this is my time. Okay, so this is my time. So with a single antenna, you are receiving these symbols at each time. So, right. So this is the estimate which we derived earlier, which is X transpose X inverse X transpose Y. So our answer is first. Any doubts? Okay. Second problem. So now we are given that we have N is 4. So what is N is 4? This is my time, right? So we have 4 symbols at 4 different time instances. And what are these symbols? So these are X1. X1 is at time 1. Okay, X2 is at time 2. X3 is at time 3. And X4 is similarly at time 4. Okay, so you need to first identify at which time period which symbol is being transmitted. Okay, and we are given that the received vector is like this, right? So if you just see this, so this means that at the receiver only one antenna is present, and this one antenna is capturing these 4 symbols, right, as given in the question. And okay, so first we try to make the pilot matrix. Okay, try to write down the pilot matrix from the information given in the question. So if you see, the first value is 2 minus 2, right? So 2 minus 2, this is our, so just remember that the time is in the row. Okay, that the time comes in the row, whereas the column is my antennas. Okay, so all the antennas are placed in the column, are placed column wise, and each symbol which they are transmitting are placed in the row wise. Okay, so so X1 comes in the first row, X2 comes in the second row, X3 comes in third row, X4 comes in the fourth row. Now what has been asked, right? So is this matrix invertible? So this is a, so this matrix is a 4 cross 2 matrix, right? X is a 4 cross 2 matrix, and this is not invertible because it's not a square matrix, right? So the first option is wrong, right? So this is not invertible. Okay. Does it have identical columns? That is, are the columns equal to each other? So no, right? So you can just observe that the columns are not identical to each other. Then does it have orthogonal columns? What is the meaning of orthogonality? Orthogonal. So what is the meaning of orthogonality? That is, say x of column 1, okay, and if you multiply it with the transpose of column 2, right, such that this is kind of a dot product again. Okay, this is the dot product of the columns, right? Is it 0? So that means orthogonality. So orthogonality also means kind of independence, right? So both columns are independent of each other. So you need to check that. So let's check that, right? So if you see, okay, so if you see, if you take the first column, okay, 2, 3, 2, 2, and if you multiply it with -2, 2, -3, 2, right? This is my first column, right? This is my column 1, and this is my column 2 transpose. Okay, this is my column 2 transpose, and if you multiply, you get -4. It is 2 into -2, then 3 times 2 is 6, and 2 times -3 is -6, and 2 times 2 is 4 again, right? And if you solve this, this comes out to be 0, right? So that is what, so it is orthogonal, it has orthogonal columns. Any doubt in this problem? Any doubt? No? Okay. So now it again, so this is a build up to the previous question. Again, we are given the same symbols x1, x2, x3, and x4, right? So my x matrix is still this only. Okay, so just keep this in mind. And now we have been asked what is the pseudo inverse of the pilot matrix X. So how do you compute a pseudo inverse? So pseudo inverse is this part, right? Not the Y. So this is my pseudo inverse, X transpose X inverse into X transpose. So first we need to multiply X transpose into X, right? So what is X transpose? So this is my X transpose matrix, and this is my X matrix. And if you multiply them, right? So this is what this is a 2-row 4-column matrix, and this is a 4-row 2-column matrix. So you end up with a 2 cross 2 matrix. You end up with a 2 cross 2 matrix. And if you solve, if you multiply X transpose X, so this is what you get. So what is 4 plus 9 plus 4 plus 4? So this is 21, right? And so what you will be getting, so you will get this, like 21, 0, 0, 21. This is the 2 cross 2 matrix which we are getting. Okay. Now what do we need? We need to now compute the inverse of this matrix. Okay. What is the inverse of this matrix? So the inverse of this matrix will be basically 1 by 21, 1001. Okay. So I hope you know how to compute the inverse, right? So you need to find out the determinant, and then you need to find out the cofactors of each part. Okay. And then finally, for the pseudo inverse, now this X transpose X inverse is again multiplied with X transpose, right? So basically what you have is 1 by 21, and X transpose is, this is my X transpose. Okay. So you basically get A. Any doubt in this question? Please feel free to, raise hand and ask. Anybody? No? Okay. Okay. Now this is again a build up to the previous two questions. and we still have the same X pilot matrix, right? X1, X2, X3, X4, and we have the same Y. So now what we need to compute, we need to now compute the ML estimate. What is my ML estimate? So my ML estimate is my pseudo inverse times Y. Right? This is a pseudo inverse into Y vector. Right? Pseudo inverse multiplied with Y vector. So this was the pseudo inverse which we computed in the previous question. And if you multiply this with the Y matrix, right? And if you solve this, so this is basically a 2 cross 4, and this is a 4 cross 1. Okay, so you end up with a 2 cross 1 matrix. And if you solve this, you get 1 by 21, 2 and 19. So 2 by 21 and 19 by 21. So again, A is the right answer. Any doubts to anyone? Okay. Next question. Again, we have the same X, X1, X2, X3, and X4 as they were above. And the Y is also same as above. And we are given the noise variance is -6 dB. So you must be now familiar with this. So if you are given sigma square in dB, you need to convert it in watt, sigma square in watt. And how do you do that? So 10 log 10 sigma square in watt, and this is -6. So sigma square in watt is 10 to the power -6 by 10. This is approximately 1 by 4. Okay. So what are we asked? So we are asked to compute the covariance matrix of the MLE. Okay, what is the covariance matrix? So as we saw in the derivation, this is sigma square into X transpose X inverse. So X transpose X inverse was this, right? 1 by 21, 1001. And sigma square is, as we computed here, this is 1 by 4. So 1 by 4 times this is 1 by 84, 0, 0, 1 by 84. Okay, so option D is the right answer. Any doubts? Okay. Question 6. So we still have the same problem as above, right? So X1, X2, X3, X4 are same as above. And Y is also same as in the previous questions. Noise variance is -6 dB, same as previous questions. The variance of estimates of individual channel coefficients. Okay, so if you see, this is my covariance matrix, which we got in the previous question. So just try to recollect. So if you have like expectation H transpose, right? So this is say A 0, 0, some B, right? So this is your variance of H1, right? This is the variance of H2, right? This is my covariance of H1, H2. Similarly, this is the covariance of H2 and H1, right, which are zeros in this case. So what we have been asked, what are the variances of the individual coefficients, which is A and B, and in this case both are 1 by 84 each, and so the answer is 1 by 84. Okay, any doubt? Right. So this is still the same signal model, X1, X2, X3, X4, right? Y is also same, the noise dB is given. And what is the correlation between the channels, right? That is what has been asked. And as we discussed here, that is the correlation, or so the correlation is the non-diagonal elements. Okay, so the non-diagonal elements. Okay, and these are 0 in this case, so the answer is 0. Right. Right. So consider a multi-channel, multi-antenna channel estimation. So when are the estimation errors of various channel coefficients uncorrelated? Okay, so when are they uncorrelated? Okay. So when the pilot matrix is square, so is it necessary that the pilot matrix, which is X, it has to be a square matrix? No, right? So we saw that if X is a n cross m thin matrix, then also you can compute the channel coefficients, right? How? To the pseudo inverse matrix. So that is why this is not necessary that the pilot matrix has to be a square matrix. This is not necessary because we are using the pseudo inverse manipulation. Then when the columns of the pilot matrix have the same norm, okay. So of course column matrix do not need to have the same norm. Okay. And when the columns are orthogonal to each other. So again, so what is asked? When are the individual coefficients uncorrelated to each other? Okay. That is, say we have an X matrix. Say you have A, B, C, D, and you have some elements E, F, G, H. Okay. Now you will be having this the the covariance matrix, right? And since we have two antennas or two channel, right? So H1, H2. So say this is some A, B, C, D. Right? So when will B and C be zero? Right? B and C will be zero, right? If the channels are independent to each other, right? Independent to each other. So for independence, the columns should be orthogonal to each other. What is the meaning of? So we saw a numerical above, which was just a minute. Yeah. So this was my X matrix. If you just remember this problem, so we computed the dot product of the X matrix of the columns of the X matrix, which came out to be zero, right? So the columns of the X of the pilot matrix, they need to be independent to each other, and so they need to be orthogonal so that the so that the channels estimation errors are uncorrelated to each other. So option C is the right answer. Okay. Right. Question 9. This is a very interesting question. So we have 10 pilot vectors, right? N is 10. And now we are given a form of xk. I'll just write it for clarity. So this is 1 minus 1 k minus 1. Okay. Right. So let's see if k is 1. Okay, if k is 1, substitute k here. If you substitute k in this problem, so you have 1 remains as it is, but the second element is now minus 1 to the power 1 minus 1, which is 0, right? Minus 1 to the power 0. And what is any number to the power 0, which is 1 itself. So the first element is minus 1, 1. Okay. Now, if k is 2, you have 1 again. But now what do you have? You have minus 1 to the power 2 minus 1. Okay. Minus 1 to the power 2 minus 1. So minus 1 to the power 1, which is minus 1. Okay. So if you see that the first element or at any time which is being transmitted is always 1. But the second element is toggling between 1 and minus 1, right? So it is at k is 3, it will be 1. At k is 4, it will be minus 1. Similarly, at k is 10, you will have minus 1 to the power 9 minus. So it will be at k is 10, you will have 10 minus 1, which is minus 1 to the power 9. which is -1. Okay. So yeah. So now we first had to generate the pilot matrix, right? And we were given a general formula for the pilot matrix, and we used that general formula to first write down the pilot matrix. So we have now written down the pilot matrix. Now what do we have to do? Now we need to find out the ML estimate. Okay. So we need to compute X transpose, X inverse, X transpose, which is what? Which is my pseudo inverse. Okay. So first we compute a pseudo inverse. So this is a fairly straightforward problem. So now the only challenge was to generate the pilot matrix. So this is our pilot matrix, right? So you have the first column is all ones. The second column is each element is toggling between 1 and -1. So if you just solve it, you will get 1/10 and you get this matrix. It's the same matrix, actually this is a transpose of that matrix. Okay, but if you just solve this, uh, solve it in a clean paper, okay, it is fairly simple. And finally, see what we are given is that y are y1, y2 up to y10, right? These are the y's which are given. So if you want to compute the channel vector, so you need to now multiply y with this pseudo inverse. Okay. So now what will happen is, so if you see, okay, shall I write? I think let us just do one thing. Okay. Yeah. So see, we obtained this pseudo inverse X transpose X inverse X transpose as 1/10. And this matrix, right? This is some matrix 1, and this is all ones, and this is toggling between 1 and -1. Okay. And now we have to multiply this with y, right? This has to be multiplied with y. So 1/10, 1. These are all ones, and this is toggling between 1 and -1. And what we have here is y1, y2, so on up to y10, right? This is what we need to do, and this will give my h hat, right? I hope it is clear. So what you will get is, just see, so the first row, each element of this row will be multiplied with each column, or each element column. So what you will be basically getting is y1 plus y2 plus y3 and so on to y10, right? And the second, what you will be getting is y1 minus y2, okay, plus y3 and so on minus y10. Okay, I hope this is clear. If anyone has any doubt, can you just raise your hand. So what is this? This is basically 1/10. And if you just see, this is summation over all yks, right? The first element, whereas the second element is actually y1 minus y2 plus y3. So it's again the sign is toggling, right? So this can be represented as summation -1 to the power k minus 1 into yk. And what is 10? 10 is my n, right? So this becomes 1/n. And the first element is yk, and the second element is -1 to the power k minus 1 into yk. So that is why the answer is the fourth one, that is D part, right? So this is what I had written here, but just to elaborate. Okay. Any doubts? Any doubt? No? Yeah. So now this is the last question. So we have again, this is the previous signal model. So we have again 10 pilot signals. This is our xk, which is the toggling X pilot matrix, and we have to find out the covariance of the ML estimate. So now our AWGN variance is 3 dB. So we compute first the sigma square in watts. So 10 to the power 3 by 10, and this is approximately 2. Okay, so what is my formula? We have sigma square x transpose x inverse, right? So we need to compute this sigma square x transpose x inverse. We derived this earlier. And what will be x transpose x inverse? So x transpose x inverse comes out to be 1 by 10, 0, 0, 1 by 10. So do you need help to solve this? I believe it is straightforward, right? So you have just a minute. Yeah. So you have x transpose. So these are all ones. 1 minus 1. So 1 minus 1. And similarly, you have all ones. 1 minus 1 minus 1. So this is x transpose x. Right? You will solve this. Right? And similarly, you will then take its inverse and right. So that's all you have to do, which is x transpose x and its inverse. Right? And the sigma square is 2. Right? So you just fit 2 here and we get 1 by 5, 1 by 5 in the diagonal elements, and the rest are 0. So this is our answer. So any doubt in any question? Yes, someone is trying to ask. Yeah, go ahead, please.
Actually, in quiz which is mentioned on week 4, there is a concept of sigma square h. We couldn't understand. Can you elaborate on that?
Sigma square h. The current week 4?
Yeah, current week. Yeah. If
Sigma square h. Okay, let me see that. So, okay, let me just close the recording and I'll see the question, right? Because I don't know the question. Just a minute. Okay, thanks.